The Drake equation was developed by American astronomer Frank Drake in 1961 as part of an effort to guide discussions at the first scientific meeting on the search for extraterrestrial intelligence. Let's break down each term in the equation. The number of communicative civilizations. This is the final result of the equation, representing the estimated number of extraterrestrial civilizations in the Milky Way galaxy that could communicate with us via radio or other detectable signals. It depends on the multiplication of all the different factors, the rate of star formation in the galaxy. This term represents the number of stars formed per year in the Milky Way galaxy. Current estimates suggest that about 1 to 3 new stars are born each year. This number sets the stage for determining how many of these stars might eventually host planets with life. The rate of star formation provides the raw material for the potential development of life. Fraction of stars with planets. This term is the fraction of stars that have planetary systems. Thanks to advances in exoplanet detection, especially from missions like Kepler, it's now known that most stars host planets, with estimates ranging from 0.7 to 1.0. This term highlights the number of Earth-like planets per planetary system. This term refers to the number of planets per planetary system that are within the star's habitable zone, where liquid water could exist, often called the Goldilocks zone, not too hot, not too cold. For example, Earth is in this zone in our solar system. The habitable zone varies depending on the type of star and planetary conditions. Estimates for Ni are still being refined, but there are believed to be numerous planets in this zone around many stars. Fraction of habitable planets, where life actually arises. This term reflects the probability that life actually originates on a planet. While Earth shows that life can develop under favorable conditions, we have no concrete data for other planets. This factor is very uncertain and could range from almost 0, if life is rare, to close to 1, if life arises readily under the right conditions. Fraction of planets, where intelligent life develops. Among planets where life has arisen, this term estimates the fraction where that life evolves intelligence capable of building technology. On Earth, intelligence evolved in only one species out of millions, which makes this number highly speculative. It could be a rare or common occurrence, depending on the evolutionary pressures and environmental factors on other planets. Fraction of civilizations that develop technology to communicate. Even if intelligent life arises, not all civilizations may develop technology for interstellar communication, like radio signals. For example, humans have only been capable of sending detectable radio signals for about 100 years, which is a tiny fraction of our existence. This term accounts for how many technologically advanced civilizations might exist. Length of time that civilizations release detectable signals. This term is critical because even if a civilization develops the ability to communicate, it may not do so for long. Factors like self-destruction, nuclear war, environmental collapse, technological changes, or deliberate non-communication, civilizations going dark for safety reasons, could limit how long a civilization's signals are detectable. L represents the average lifetime of a communicating civilization, and it could range from a few hundred years to millions of years. Most of the variables in the Drake equation are highly uncertain. Some of them, such as the fraction of planets where life arises or the likelihood of intelligence evolving, are based entirely on speculation, as we have only one example of life, Earth. The range of possible outcomes for N varies from 1, only us, to millions or more, depending on how one estimates the variables. The equation serves as a framework to guide our thinking about the various steps that might lead to communicative extraterrestrial civilizations. It also underscores why we might not have detected alien civilizations yet, a problem known as the Fermi Paradox. Even if there are many civilizations, vast distances and short windows of communicative activity may prevent us from finding them. While the Drake equation was originally formulated based on very little data, modern discoveries of exoplanets, advances in astrobiology, and ongoing efforts like the SETI project have given us a better understanding of some variables, especially R star and FP. However, the speculative nature of FL, FI, and L means the equation is still largely used for educated guesses rather than precise estimates.